It's quite possible that an Italian astronomer looked through this telescope at a star-filled sky 400 years ago and in the process saw things no human had seen before.
Observers such as Galileo and others started to observe and report things in the sky which were not in the old texts that had been the authority up to this point in time.
Dating from about 1630, the Italian-made telescope is the oldest outside of Europe. The first telescope had been invented only a few decades earlier, and in a portrait from 1636, created while he was still alive, Galileo himself is seen holding a similar instrument.
This telescope testifies to the very early days of the telescope when the instrument was revolutionizing the way we do science and the way we learn about the universe.
Hi everybody, Chris Helms here from the Adler Planetarium. I'm the collections manager. Today I want to show you the oldest telescope in America. In fact, it's the oldest telescope outside of Europe. It was made sometime between 1630 and 1640 in Italy, and is part of a group of about 20 telescopes thought to be from before 1650. The earliest documented demonstration of a telescope dates from 1608, which makes this one of the only surviving representatives of the first generation of telescopes ever made. The tube of the telescope is formed by 5 draws made of pasteboard decorated with gold-tooled leather. The eyepiece is unfortunately missing, but it comes with what we believe to be the original object glass. There are ink markings on the tube so that the draws can be extended to give the correct focal length. On the basis of these markings, we can infer that this telescope gives a magnification of about 10 times. Have you ever wondered what telescopes Galileo would have looked through to stargaze at night? Here in front of me I have 2 examples of telescopes he actually might have used. First one is a replica made for us in Florence, Italy in 1930. This was made for the grand opening of the Adler Planetarium and is an exact replica of a Galilean telescope on display in Florence. The second telescope in front of me here is the oldest telescope known to exist outside of Europe. It was built in about 1635, and there's only a couple dozen of them known to exist from before 1650. This is an exact type of telescope that would have been made in Galileo's workshop and used by Galileo and used by early astronomers across Europe. You can see both of these on display at the Adler Planetarium permanently, so anytime you come and visit, they'll be here.
Call him the telescope hunter. Marvin Bolt's on a mission to find, catalog, and peer through the world's oldest telescopes.
When you shine light
About a decade ago, researchers knew of only 10 existing telescopes made before 1650. Backed by government grants, Bolt and a colleague began looking for more. The hunt has led him to 21 countries.
So now we found about 25 to 30 of those, and over 1,000 telescopes made before 1750.
Today, the most powerful telescopes allow us to travel to the farthest reaches of space. 400 years ago, the view wasn't quite as spectacular. Bolt took this photo through a telescope from 1620.
We have to really look through them to see how good are they.
Some of these very old telescopes are on display at Chicago's Adler Planetarium. Bolt worked there before coming to the Corning Museum of Glass as science and technology curator.
The purpose of this is to block off the portions of the lens which are less than perfect.
This telescope dates to around 1630.
It's constructed mainly of pasteboard and leather, tooled leather, so it's a lovely example of these early telescopes.
Bolt's research magnifies the telescope's scientific, military, and cultural significance. Production took off around 1750 with the addition of a second piece of glass to the lens.
It enabled people to see farther and deeper into the universe, but also to spy on each other, maybe for military purposes or just to check out what the neighbors were doing.
Bolt estimates there are several hundred old telescopes left to discover and catalog, so his focus will remain on these astronomical artifacts. Michael Rubenkamp, Associated Press, Corning, New York.
So there's a nice
Vom discuta despre cel mai ambițios proiect constructiv realizat anul acesta, luneta de 34 cu focala de 1,8 metri lungime. Este cea mai lungă lunetă construită anul acesta. Toată luneta este realizată din cupru. Cum puteți privi, la capătul lunetei se află partea de focusare, iar în față este locul în care se va monta lentila obiectiv. Acesta este adaptorul de prindere a lentilei. După cum puteți observa, avem și lentila obiectiv șlefuită de Tavi Florian. Este o lentilă biconvexă simetrică de o calitate foarte bună. Este a doua lunetă construită la observatorul nostru folosind lentile șlefuite de Tavi Florian. Extrem de bune, de o calitate extraordinară. Puteți observa cum mărește obiectele la îndepărtare. Cu cât îndepărtezi lentila de observator, mărește din ce în ce mai mult, până la punctul în care se va focusa lumina. Urmează vopsirea diafragmelor interne care reduc din reflexele parazite ale țevii de cupru pentru a produce imagini cu contrast ridicat. Fără aceste diafragme, imaginea este complet încețoșată. Pentru a reduce din reflexii trebuie să le montezi într-o anumită ordine. Mai întâi trebuie șlefuite până devin mate, iar la final se vopsesc cu un spray negru mat. A fost nevoie de 2 straturi aplicate pentru a fi sigur că sunt perfect mate. Iar la final se introduc în interiorul tubului optic într-o ordine foarte bine aleasă, operațiune care a durat aproape 2 ore jumate. Este foarte greu să le introduci, apoi să verifici dacă aranjamentul lor este perfect simetric și egale una față de cealaltă. Au fost învelite într-o bandă izolantă pentru a intra mai greu și apoi au fost forțate în interior. Aproximativ 18 diafragme au fost nevoie pentru a reduce din reflexiile parazite ale tubului optic. Deci un număr foarte mare de diafragme și a durat mult până ce fiecare a fost testată, vopsită, șlefuită, învelită în acel adeziv special și introdusă la locul potrivit. Deci a durat ceva timp până s-au introdus toate aceste diafragme. Iată la final cum arată interiorul tubului optic după ce toate diafragmele au fost instalate. Vedeți că reflexiile au dispărut, iar luciul tubului nu mai există. Acele reflexii care le vedeți din interior sunt nesemnificative. Iată, în interiorul tubului optic, văzut cu lanterna telefonului, puteți observa numărul mare de diafragme. Aici este asamblarea focuserului pentru oculare de 1,25, implicit inserarea adaptorului pentru ocularele, având o deschidere sau un diametru de 1,255. Focusarea se face prin mișcarea ocularului înainte și înapoi în tubul portocular. Acela este lipit și atașat definitiv la tubul optic. Este un fitting din cupru, o reducție de la 42 la 35 mm, iar în interior se află un adaptor care reduce la 31 mm în diametru, potrivit ocularelor, având un standard de 1,255. Aproape o zi întreagă a durat asamblarea lunetei, de la montarea celulei obiectivului până la inserarea diafragmelor și montarea lunetei pe montura EQ1. Iată o diafragmă pregătită pentru inserare. Este un tub PVC de 40 mm în diametru, șlefuit pe interior și vopsit negru mat. Acela va fi inserat la urmă. În total, 18 diafragme care reduc din reflexiile parazite ale țevii de cupru, pentru că toate țevile de cupru în interior sunt foarte lucioase. Urmează operațiunea de atașare a lunetei pe montura EQ1. Am venit cu o scândură foarte dreaptă pe care am montat-o de un adaptor de fixare pe montura EQ1, deci sunt 2 adaptoare, iar la final am venit cu țeava de cupru prinsă folosind 4 coliere de prindere. În imagine avem doar 2 pentru testare. Această montură nu este foarte bună pentru că luneta e foarte lungă și am observat că se produc deformații ale tubului optic datorită frigului și a diferențelor de temperatură. Deci luneta este prea mare pentru a fi montată pe montura EQ1. Iată soluția. Montura pe 2 puncte de sprijin. Aceasta este ultima construcție realizată după terminarea lunetei. Montura pe 2 puncte de sprijin, totul este homemade, în afară de trepiedul de la capăt. În față avem o montură folosind o ramă care se poate coborî și înălța pentru a ajusta înălțimea tubului optic în funcție de locația la care se află obiectul pe cer. Iar la capăt avem un sistem ingenios folosind un trepied și un sistem mecanic pentru a mișca luneta. Este un tip de montură care distribuie uniform greutatea, dispar vibrajele puternice induse de monturile având un singur punct de sprijin, iar pe 2 puncte de sprijin luneta se așează comod, fără ca tubul optic să se îndoaie. Deci este o montură foarte bună pentru observații astronomice folosind lunete lungi. În secolul al XVII-lea, astronomul Galileo Galilei a fost cel care a observat pentru prima oară craterele lunare. Această revoluție a schimbat astronomia. Luneta pe care Galileo a folosit a fost o lunetă Simplet, folosind 2 lentile. Lentila obiectiv, cât și ocularul, o lentilă negativă. La obiectiv a folosit o lentilă plan convexă sau biconvexă. Aceste 2 tipuri de lentile erau folosite în secolul al XVII-lea la obiectiv, iar ocularele la început au fost negative, folosind o lentilă plan concavă. Observațiile au fost foarte dificile pentru că câmpul vizual este foarte mic cu această configurație, iar astronomul care folosește un astfel de instrument observă o porțiune foarte mică pe cer, iar căutarea obiectelor cu un astfel de instrument este foarte dificilă, datorită distanței focale mari și a câmpului vizual extrem de mic. Totuși, chiar și cu aceste limitări, Galileo a reușit să observe lucruri interesante pe cer nemai observate de nimeni. De la fazele lui Venus până la sateliții lui Jupiter și forma lui Saturn, toate au fost descoperite de Galileo, cât și petele solare. A observat că cerul este brăzdat de stele mult mai slabe decât cele pe care le poate observa ochiul uman. După moartea lui Galileo, astronomia a evoluat. Practic, lentilele au devenit din ce în ce mai bune. Nu se cunoaște modalitatea de fabricație a acestor lentile obiectiv, modalitatea de testare, fabricație și multe altele. Acestea sunt lentile realizate de Christian Huygens, aparținând telescoape areale, având focale foarte lungi. Se cunosc câteva ipoteze legate de producerea acestor lentile obiectiv. Iată un telescop refractor mic din secolul al XVII-lea. Aceste lunete Simplet, folosind obiective având o singură lentilă, au funcționat chiar și până la jumătatea secolului al XVIII-lea, deci au avut o durată de viață îndelungată. Lentilele erau fabricate folosind sticle venețiene produse în Italia, probabil cele mai bune din lume pentru aceste instrumente. Apoi erau șlefuite de diverse matrițe metalice, având diferite raze de curbură, folosind abrazivi duri până la cei mai fini, apoi erau polisate folosind o piele de cerb, între care era depus un praf special numit tripoli. Nu se cunosc mișcările de polizare. Pielea de cerb era montată pe matrița, care are aceeași rază de curbură precum a lentile obiectiv, iar între ele erau introduse acel praf pentru polizare numit tripoli. Nu se cunosc mișcările folosite de opticieni, metoda de testare a lentilor nu se cunoaște. Acest proces este descris în cartea lui Torricelli, iar multe dintre aceste secrete nu se cunosc. Acesta este doar o frântură din acest proces de fabricație a lentilelor optice. În ziua de azi, aceste lentile sunt testate în diverse laboratoare pentru a vedea calitatea lor optică, suprafața lor, cât și calitatea sticlei folosite pentru fabricația acestor obiective. Aceleași procese erau folosite la fel și în producția de oculare. Iată minunea astronomiei românești, luneta de 28 mm cu focala de 1250 mm, prima lunetă Simplet construită în România, având totodată o construcție definitivă, folosind o țeavă de cupru. Puteți vedea reflexia lentilei obiectiv, având diametru util de 27 mm, țeava de cupru are un diametru exterior de 35 mm în diametru. Este de fapt o lunetă lungă destinată pentru observații planetare, lunare și la stele duble. Diametrul lentilei este de 35 mm, iar diafragma din față o reduce la 27 mm pentru observații astronomice. Produce un coeficient de 1,7 al aberației cromatice, practic se comportă ca un acromat. Țeava este din cupru, foarte dreaptă, prinsă de o scândură cu 3 coliere de prindere, montată pe montura EQ1. Este un instrument foarte bun. Acest telescop refractor, de fapt, este instrumentul de bază, pentru că un astfel de refractor îți oferă imagini foarte clare, având o claritate foarte bună, turbulența atmosferică nu este așa puternică, iar poți să faci observații foarte bune, terestru, cât și astronomic, până la o putere de până la, să spunem, 120x. Deci funcționează la o putere foarte mare și chiar depășește de 3 ori diametrul obiectivului. Calitatea optică este excepțională. Lentila obiectiv este din sticlă BK7, iar prelucrarea este incredibilă. Aici Tavi Florian a făcut o treabă superbă. Iată produsul finit, o lunetă superbă pentru observații la lună, stele duble și planete. Foarte frumos se vede prin această lunetă. Merită să vedeți. A doua minune a observatorului nostru, luneta de 34 mm, tot dintr-o lentilă șlefuită de Tavi Florian. Iată ce monstru! Urmașa lunetei de 27 mm. Cea mai mare lunetă construită la observatorul nostru, montată pe 2 puncte de sprijin. Diametrul 34, mult mai mare decât 27, într-adevăr, având o focală de 1,8 metri. Cu cât este mai mare diametrul obiectivului, focala trebuie să fie din ce în ce mai lungă, aproape de 3,5 ori. Aici este un sistem de montare al ocularului, folosind un adaptor pentru smartphone, pe care poți atașa telefonul, se prinde de țeavă sau de tubul portocular. În general se prinde de oculare, dar având în vedere că e foarte lungă luneta, acest adaptor pentru filmări la ocular este montat direct pe țeavă și mai ales pe tubul portocular. Am modificat un pic adaptorul smartphone pentru a se potrivi cu telefonul pe care l-am. Iată și instrumentul. Modul de observare este interesant pentru că ai de ajustat 2 puncte de sprijin. În față avem o ramă care se poate coborî și înălța, iar la partea din spate un sistem format din 2 plăci laminate care efectiv le miști ca o montură Dobson înainte și înapoi stânga-dreapta, iar tot sistemul ăla cu trepiedul este pentru a susține luneta. Poți să faci și de acolo ajustări foarte fine, folosind controlele slow motion ale monturii altazimutale. Vedeți sistemul de montare la bază, folosind 2 plăci laminate, care le miști frumos, n-ai treabă, funcționează foarte bine. Asta este sistemul, deci așa funcționează. E un sistem foarte ingenios de prindere a lunetei. Pentru că dacă nu ai un sistem de 2 puncte de sprijin, cu o țeavă de 1,8 metri, îți dai seama ce lungă este luneta, se poate îndoi dacă folosești un trepied. Am și testat trepiedul EQ1 pe această lunetă și nu prea mi s-a potrivit, adică tremura foarte tare și se producea multe deformații la temperaturi foarte scăzute. Iar cu acest tip de montare pe care îl vedeți, nu mai avem probleme legate de îndoirea tubului sau de vibraje. Totul funcționează perfect. Puteți vedea și filtrul solar în fața lentilei obiectiv. Este locul potrivit și ideal pentru montarea unui astfel de filtru. Am făcut niște mici găuri în tubul optic pentru a putea aerisi mai bine interiorul țevii, pentru că este foarte lungă și sensibilă la aclimatizare. Am observat acest lucru mai ales la temperaturi reci. Dacă o scoți din casă la 25 de grade și observi cu ea afară, să zicem la 10 grade, trebuie să aștepți mai mult timp până ce se răcește și aerul cald iese din interiorul tubului. Proces care durează. Cu cât este mai lung instrumentul, cu atât durează mai mult. Iar acest proces se poate scurta folosind diferite metode. Cea pe care am ales-o este de a face niște găuri în interiorul tubului pentru o aerisire mai bună. În 7 minute, la 10 grade, este complet aclimatizată. Am observat multe chestii faine cu această lunetă. Benzile de nori ale lui Jupiter, foarte frumos. Am văzut și detalii între benzile de nori. Toate cele 4 benzi de nori se vede. Foarte ușor, la o putere de 100x. Merge chiar și până la 144x. Deci o putere de aproape 4 ori cât diametrul obiectivului. Deci lentila este foarte bună. Pe lângă Jupiter am observat Saturn, se vede foarte frumos inelele. Luna, o splendoare, detalii foarte fine, imagine extraordinară. Multe stele duble am văzut, foarte frumos se prezintă la stele duble, deci foarte bine funcționează. Iată partea din spate a lunetei cu montarea finală. Arată frumos, nu? Deci este o lunetă foarte mare față de celelalte pe care le-am avut. Acela este ocularul, mișcarea de focusare se face înainte și înapoi. Focusarea nu e așa sensibilă la aceste lunete de focală foarte lungă. Deci nu trebuie să avem probleme cu focusarea pentru că imaginea rămâne focusată chiar și 1 centimetru dacă deplasezi ocularul înainte și înapoi. Deci aceasta este luneta. Țeava din cupru are un diametru de 42 mm și efectiv avem aici un sistem care ne permite înălțarea și coborârea tubului optic în funcție de înălțimea la care se află obiectul observat, iar de la capăt putem să ajustăm partea de urmărire a obiectului folosind cele 2 placaje pe care este montat trepiedul. Dar se poate folosi și controlele slow motion de la trepied pentru a fixa ținta sau obiectul în câmpul vizual mai finuț. Este un sistem având 2 puncte de sprijin foarte ok și indicat pentru astfel de lunete foarte lungi cu focale foarte mari. Iată soarele la 72x printr-un ocular de 25 mm Kellner. Este prima oară când facem observații cu un adaptor smartphone la așa lunetă și pot să spun că nu sunt așa de mari vibrajele. Iată cum am atins luneta. Nu sunt vibraje foarte mari față de ce a fost înainte. Coșmar, deci dacă atingeai, nu se mai oprea 10 secunde. Foarte repede se stabilizează imaginea, câteva secunde și s-a oprit vibrajele, deci sunt foarte puțini, nu este nicio problemă cât ține. Se poate observa o pată solară aproape de mijlocul soarelui. Acestea sunt de fapt zone active mai reci pe suprafața soarelui, unde câmpul magnetic este foarte activ. E ca și cum câmpul magnetic străpunge suprafața soarelui. În acea zonă se află explozii solare. Se poate observa pata solară, în interiorul ei se vede o pată neagră, iar în jur se poate vedea penumbra petei solare. Soarele se rotește, așa că această pată solară se deplasează. În fiecare zi poți să vezi deplasarea petelor solare în funcție de rotația Soarelui. Dar și aceste pete, pur și simplu, pot să apară de nicăieri, se pot forma în grupuri, cresc, unele foarte mari, depinde de puterea câmpului magnetic, iar nu durează mult și dispar după câteva săptămâni. Pot să crească la diametre foarte mari și ele practic se schimbă în fiecare zi. Deci practic poți să observi schimbări la nivelul petelor solare, mai ales când sunt foarte multe la număr și sunt grupate, iar în fiecare zi poți să vezi cum se schimbă aceste formațiuni, pentru că sunt foarte schimbătoare. În fiecare zi vezi ceva diferit la ele. Acesta este avantajul observațiilor solare. Mereu se întâmplă ceva. Iată pata solară, cum apare în mijlocul câmpului vizual. Se vede partea centrală mai întunecată, dar și partea exterioară puțin mai întunecată, numită penumbra. Este zona în care poți vedea foarte multe detalii când vine vorba de petele solare, mai ales la cele mari. Aceste pete pot fi observate când activitatea Soarelui este mai mare. Ele pot fi singulare sau în grupuri, le întâlnim singure, având o pată solară circulară sau ovală, și le mai putem întâlni în grupuri. Acolo activitatea este din ce în ce mai interesantă, pentru că sunt foarte multe pete, iar cu timpul veți putea observa schimbări. Petele se pot rupe, ele cresc de la diametre mici și se fac din ce în ce mai mari, depinde de puterea câmpului magnetic, și e foarte interesant să le observăm în grupuri, pentru că acolo activitatea este foarte mare. Aici avem o pată solară cam de dimensiunea Pământului, foarte mică în relație cu Soarele. E o zonă mai activă, dar nu foarte puternică, în care sunt explozii solare. Mișcarea pe care o vedeți în imagine este datorată rotației Pământului, nu și a Soarelui. Soarele se rotește mai încet, dar ceea ce vedem la ocular este rotația Pământului. Cu cât mărești mai mult imaginea, cu atât deplasarea este mai rapidă. Aici la o putere cam de 150 de ori, pentru că am dat zoom din camera telefonului și efectiv vezi un pic mai multe detalii decât la o putere de 72x. Deci se poate, luneta e foarte bună, calitatea obiectivului e foarte bună și practic câștigi mai multă rezoluție decât la lentila de 27 mm în diametru. Foarte interesantă această pată solară, după cum puteți observa, este de mărimea planetei noastre și iată comparația petei solare față de întreg diametrul Soarelui. Imaginați-vă că acela este Pământul. Vă dați seama cât de mare este Soarele. Foarte interesant. Iar calitatea imaginii prin această lunetă pot să spun că este foarte bună. Stelele sunt excepționale. Iată steaua Arcturus la putere de 144x. Prin această lunetă se vede acel airy disk frumos. La aceste obiecte strălucitoare precum stelele, aspectul lor este minunat prin aceste lunete Simplet. Acel airy disk rotund, gălbui, înconjurat de un inel de difracție, este fenomenal. Imagini superbe. Acel inel de difracție, de fapt, este produsul lentilei obiectiv. Acest efect este o iluzie, practic nu vezi steaua, ci acest efect de difracție, datorat distanței focale foarte lungi. Steaua implicit nu se poate vedea suprafața stelei, n-ai cum să o vezi. Nici cele mai mari telescoape din lume nu pot vedea. Dar acest efect se poate observa și este foarte frumos să observi acest airy disk cu adevărat spectaculos. Se vede mult mai clar la ocular decât ceea ce poate obține o cameră foto. Imagini spectaculoase, la stele duble. Îți taie respirația aceste aerodiscuri, care pot fi observate chiar și la 72x, începând cu 50x, 50 de ori. Aici e la o putere de 144x. Mizar, o stea dublă foarte luminoasă. Iată planeta Saturn la 144x. Se pot observa inelele și spațiu dintre inel și planetă. Chestia este că rezoluția este foarte slabă la aceste camere video, iar practic la ocular imaginea este mult mai spectaculoasă. Folosind o cameră smartphone, dacă dai zoom apare zgomotul de imagine și acesta e foarte greu de înlăturat doar prin procesare video. Totuși, vizual se vede foarte bine. Chiar sunt mulțumit să vezi inelul la 144x folosind o cameră smartphone. În unele momente se poate vedea mult mai clar planeta. Este foarte greu să ții camera în mână filmând la ocular. Foarte greu. Trebuie să stai nemișcat. De aceea este nevoie de un suport smartphone pentru a-ți îmbunătăți performanțele și practic să nu mai fii nevoit să ții camera în mână. Ea trebuie să fie perfect centrată în câmpul ocularului. Iată steaua Arcturus din nou, la o putere de 300x de această dată. Aceste camere smartphone, odată ce le pui la ocular, îți micșorează puterea de mărire și trebuie să dai un extra zoom, altfel obiectul se va vedea foarte mic. Chiar dacă în ocular obiectul este foarte mare, camera îl micșorează. Uitați ce frumos este inelul de difracție și în interior se află un disc aerii, verzui. Inelul de difracție rotund este de culoare roșiatică, ștearsă, și este perfect circular în jurul inelului de difracție. Asta înseamnă că luneta este bine colimată. Iată și minunea astronomiei târgu-mureșene. Luneta de 34 mm folosește două diafragme, una de 34 și una de 35 mm. Două folosesc la 34 pentru că ai rezoluția cea mai bună, de 3,5. Iar uitați ce frumos arată suportul, tot construit acasă. O zi întreagă s-a muncit la această lunetă pentru a asambla, iar într-adevăr a meritat. Este o lunetă foarte bună. Probabil și ultima construită, pentru că cu o lungime mai mare, de 2 metri, să spunem 2,5 metri, acest sistem, pe două puncte de sprijin, încet devine instabil. Devine din ce în ce mai greu. Iar la lungimi de peste 2,5 metri, acest sistem de montare a lunetelor lungi nu mai este fiabil. Începe deja să tremure și să producă diverse vibraje. Încetul cu încetul, sistemul nu mai funcționează la focale de peste 3 metri, producând deformații ale tubului optic. Deci limita este la 2,5 metri lungime. La peste 3 metri este nevoie de un sistem de scripeți și funii pentru a stabiliza tubul optic. O metodă de montare care necesită un stâlp montat permanent în mijlocul curții, la care luneta să fie permanent susținută. Aceste monturi pe două puncte de sprijin sunt relativ portabile în curte, dar această lunetă de 1,8 metri nu este portabilă când vine vorba să o duci undeva. Este o lunetă care se pretează foarte bine în curte. Este foarte dificil să demontezi toate aceste componente și să le duci cu mașina. Este o lunetă foarte bună pentru observații astronomice la stele duble, lună și planete.
The aristocratic Republic of Venice had been a great maritime power for centuries. Commerce, crafts, ideas had blossomed there, as had the making of spectacles itself. It was still lively around 1600 in that sea-wedded state. although the center of growth was shifting west toward the Atlantic. Born into an old and talented Florentine family, Galileo Galilei was professor of mathematics in the famous University of Padua, which served the Venetian state. He was red-headed, brilliant, energetic, a superb writer, unusually gifted with his hands, a fine musician, even a good judge of wines. Galileo set up a small precision shop in his home to build apparatus for his own research. He supported the shop and the skilled artisan who worked with him by making and selling all over Europe a clever brass calculator of his own design. The two knew the busy world of the craftsmen of Venice nearby and took full advantage of their materials and know-how. The Venetians banished the smoky furnaces of their glassmakers to this nearby island 7 centuries ago. And for 400 years, Murano remained the leading glassmaking center in the world. We don't know for sure, but it's most likely that the glass that Galileo used was made here. They still make glass here in the old craftsman's way. Murano made the finest glass of its day, but modern optical glass is far superior. Lens designer Don Dilworth grinds lenses in his basement as a hobby.
To make a lens, the process is really very simple. You start off with 2 pieces of glass of approximately the right shape. And because of the motions of the grinding machine and the grinding material, the grits that you put between the 2 pieces of glass, they grind each other. So you grind these things with a fairly coarse abrasive until you generate a curve that has what you think is about the right radius. Then you clean everything up and you switch to a finer grade of grit, and you grind again for a few minutes. Then you clean up and you put even a finer grade of grit in. And when you're done, you have a surface which is the right shape, and it's very smooth, but it's not shiny yet. Suppose I want this top piece to be concave. That is, to dig out more glass in the middle and not so much on the edges. Well, it's very simple. You put the grit on the bottom one, have this be the top one, and as it moves back and forth, the edge of the bottom one is going to grind away the center of this one because the weight of this one is on the center. There's not much grinding at the edges. If I wanted to grind this the other way, so the edges were ground, I put this one on the bottom of the machine and put the other one on, the other piece of glass on top. So it's really just whichever one is on top becomes concave, and the rate at which it changes you control by how much wiggling you do, how much pressure you do, and what size grit you're using. For polishing, you make what we call a pitch lap, which is molten pitch, and you pour it over the tool. And when it's cooled just enough to have the right consistency, you put the lens on it and you press them together gently. And when it's cooled an additional amount that's just right, you put the lead weight on it, which presses the two together. And then you get the pitch lap to match the shape of the lens exactly. When you get done with the grinding, you have something which is ready for polishing. Now, instead of a grit that's rolling and grinding, the little particles of polishing compound will stick in the pitch, and they'll act like little knives that plane the glass, and they'll smooth it off. This is the most lengthy part of the process, but this is what produces the final very glossy lens surface. Galileo's case, it was strictly trial and error. They had a piece of glass. They didn't know what it was. They didn't know its properties.
In a workshop not unlike this one, Galileo first heard that a Dutch traveler had exhibited in Venice a new arrangement of two lenses that could make a ship appear close by while it was still some distance at sea. It was the telescope. Historian of science Al Van Helden has worked out the development of the telescope. So the spectacle makers did it at last.
Yeah, they finally did it. And it took them 3 centuries. Two kinds of glasses, I call them, are involved. The first one is a magnifying glass, and it dates from about the end of the 13th century, say around 1300. And it was used by aging scholars whose eyesight was getting weak, as they said then, and who used it to enlarge the print, or they didn't have print then, but the writing.
Manuscript. We saw an early painting of an old scholar wearing just such glasses.
That's right, and it was, of course, a kind of glass that you would find amongst in the scholarly community, amongst older people. When you hold it above the print, you can see how it enlarges the writing, and if you put it close to your eye, you can wear it as what we call spectacle. So that's the origin of spectacles, and that is the one kind of glass. Now, the other kind is the kind of glass that was used by young people, it still is today, to see things that are in the distance. People have this sort of weak vision of the young, as they used to call it, and that appears to make things smaller. So if you hold it above the writing, you can see it become smaller. If you take the concave glass and hold it up to your eye and look at a distant object through it, like a church steeple, you see it clearly in focus, but smaller. If you then put the convex glass in front of it, you still see things in focus and about the same size, but as you move the convex glass farther and farther away, it's like a zoom effect. The distant object appears to become larger and larger and larger, and that's as much magnification as you're going to get. And that's the telescopic effect. And I'm holding, in effect, a sort of a telescope in my hand now without a tube.
That was the size of the original Dutch telescope.
That's right. It magnified about 3 times, and it was about a foot long.
Yeah. And of course, we chose the lenses to be like that. And they had them around. They were standard lenses of the day.
That's right. These are optical replicas of lenses that they had in those days. And you could find these in the inventory of an average spectacle maker by the beginning of the 17th century. And so, therefore, following this sort of line of argument, as soon as the components became available, the instrument was invented.
So it's quite easy to make the combination, and that explains to me, as you've written, how it is that Galileo could reinvent the telescope from the rumors and the descriptions in a short time, in days or weeks maybe. And the key thing is he developed it from there.
Yes, it is what happened next, where Galileo is so important for us.
What a summer and fall of hard work they must have had, Galileo and his craftsman partner, to make the first set of telescopes. They had to find the best glass, to make lenses unknown to the spectacle makers, and steadily to improve and develop their instrument. We are lucky enough to have, from the collection of the Grand Duke himself, an instrument pretty surely of the first year of their work. When I look through at the daytime sky, I see a little bit of circle of light. Those who followed worked out many improvements of the new telescope. The improvement began with Galileo himself. He writes, "The instrument must be held firm, and hence it is good to escape the shaking of the hand, which arises from motion of the arteries and from breathing, to fix the tube in some stable place. It is best the tube be capable of being lengthened a bit, say about 3 or 4 inches, because I find that to see distinctly nearby objects, the tube should be longer, and shorter for those more distant. It is good that the convex glass, which is the one far from the eye, should be partly covered, since thus are objects seen more distinctly. With the camera playing the role of the old telescope, it is easy to accept that the threefold magnification of the Dutch telescope over the direct view was worthwhile. But it is still more striking to see the ninefold magnification of Galileo's telescope, the one that he brought to this very place to look at that very view in August of 1609. He did not stop there. He went to 20 power by November and to 30 power by January. And he entered with his telescope into that new cosmos where scientific instruments have pursued understanding ever since. It would be a mistake to imagine that astronomy began with Galileo, or with the Greeks, or with anyone else you might name. It is very old, perhaps as old as humankind. Over the long span of time, everything that can be seen today with unaided eye was noticed, even events as rare as eclipses and comets. Practical sky lore was in place. Every country person knew then what few of us know now, that the full moon always rises as the sun goes down. The skies were well understood in a different way by the mathematical, who could reckon sky positions and times very well indeed. The accurate star map in metal and the geometrically plotted sky of this 1,000-year-old Arabic calculator are witness to a sophistication beyond any simple lore. The precise calendar we use today was entirely a pre-telescopic development. Finally, there was a point of view that arose from both sources, a philosophical picture of the universe. The artist of this superb medieval mosaic in Sicily evoked it in its glowing symmetry. The philosophers said, motion on Earth is haphazard, but in the heavens it was circular, perfect. Matter on Earth is usually dull stuff, but in the heavens all was luminous. Here on Earth we know birth and death, growth and decay, but the celestial world was everlasting. From creation, our universe was split into two, the heavens from the earth. How could two such different worlds ever be one? With his first astronomical telescope, Galileo healed the split between the heavens and the earth. What marvels he saw! The moon has been rising full on the cities of the world for a long time, and on Florence's cathedral a few thousand times. But only when Galileo turned a magnifying instrument to the surface of the moon was he able to see the substance of the heavens. This is what he says of it. On the fourth or fifth day after new moon, when the moon is seen with brilliant horns, the boundary which divides the dark part from the light traces out an uneven, rough, and wavy line. There is a similar sight on Earth about sunrise, when we behold the valleys not yet flooded with light, though the mountains surrounding them already are ablaze with glowing splendor on the side opposite the sun. He could see the light change on the moon as he watched. And indeed, with a small telescope, anyone can do that now, as I have enjoyed doing many times in the past. And he goes on. Just as the shadows and the hollows on Earth diminish in size as the sun rises higher, so those spots on the moon lose their blackness as the illuminated region grows larger and larger. Sunrise in the mountains of the moon. More than that, he saw the geography of the moon. He writes, "There's another thing which I must not omit, for I beheld it, not without a certain wonder. This is that almost in the center of the moon there is a cavity larger than all the rest and perfectly round in shape. I've tried to represent it as correctly as possible. As to light and shade, it offers the same appearance as would a region like Bohemia, if that were enclosed on all sides by very lofty mountains arranged in a circle. He saw the moon as a place and he was the first artist of its landscape. The message that the moon had plains and mountains like the Earth was not the only remarkable message from the stars that Galileo wrote of when he had used his telescope. He had, a few months before the book appeared, noticed that near Jupiter, 3 faint small stars lay in a straight line. This puzzled him a little, and he duly followed it for a while to discover, to his astonishment, that those little stars were companions to Jupiter. They danced around Jupiter, sometimes hidden, sometimes there were 4, 3, 2, and they made a regular procession whose dance he choreographed in the beginning, in the first book. He was so excited by this regular and unprecedented appearance that he followed it wherever he went with his telescope, from many places, even when he made a trip to Rome. And within 2 or 3 years, he had cataloged the entire dance quite well, so that afterwards he was able to calculate a prediction for where the moons of Jupiter would be for a few months ahead. His telescope and its discoveries a sensation, Galileo came back to Florence as mathematician and philosopher to the Grand Duke of Tuscany. A few years later, while guest of a wealthy friend at this villa north of the city, he wrote of new results: sunspots, the crescent of Venus, a hint of the rings of Saturn. But it was the 4 moons of Jupiter and the mountain landscapes on our own moon that changed our view of the world forever.
All of a sudden, people lived in an entirely different world. The satellites of Jupiter were a sudden, dramatic, and marvelous discovery for several reasons. First of all, they showed that there is more than one center of motion in the universe, that the Earth is by no means the only planet, according to Copernicus, that would have a moon. No matter what system of the world you believed in, there had to be more than one center of motion. And of course, finally, it is the glamour of the discovery and the fact that Galileo tied their name to the house of the Medici.
It's true, but I guess I feel that substance is even more important than motion. The notion that the moon was made of stuff like the Earth and had mountains and rocks and was not a celestial place of some mysterious kind, that seems to me to license science to go anywhere. But I still think that the main thing is that unforgettable sentence in Sidereus Nuncius with the drawings that says, this portion of the moon resembles the plains of Bohemia, which is a direct connection between the heavenly world, or at least the lunar world, and the Earth. I think it got him into more trouble and started more speculation, and at the same time represented a bigger jump for science than anything else. Because once you say that the heavenly bodies are like the Earth in some respects, then I think you're open to pushing science out into the heavens as far as we'll go, and probably, as we now know, down into the center of matter as far as we'll go.
Yes, it's not only saying it, of course, it's demonstrating it.
Yeah.
Yes, that's also a discovery that is more accessible to the common ordinary observer. Even a modest powered spyglass will reveal the marvelous nature of the moon, and it just hits you smack between the eyes, so
Were
to
there a lot
speak.
of people doing that in that
Yes,
time?
yes. If I say 1620, I think that 5 or 6 power spyglasses must have existed by the hundreds and perhaps thousands in Europe, so that the moon was really readily accessible to not only the imagination of scientists, but the imagination of poets and what have you, and we know that from the literature.
The moons of Jupiter are harder to, well, they're not so hard to see.
No, but you need a bit more power to see them, especially in the 17th century with the small apertures, and you need more patience to work on them.
The patience is what hurts.
Oh,
you
yes.
can look at them once, but to follow them, the weather turns bad, you forget, you have to go away in the weekend, you don't
Yes.
really, I never get a good series.
That's right, with the satellites of Jupiter, it's their motion that distinguishes them with the moon. It's
a quick look that does it, that's right. So it's a sequence or a quick look, and that is a real difference.
That's right.
The publication of Galileo's telescopic discoveries made a sensation. He brought his telescopes to Rome for the first time with serious purpose. He wanted to show them in detail to his scientific peers, the Jesuit mathematicians and astronomers at the Collegio Romano. They had read the book, but now they could see the instruments for themselves. The princes and the prelates, the dukes and the cardinals, were not long behind. On one occasion, from a villa on this very hill, he invited the party to look through his magnifying tube at a distant, familiar church. They could see it in all detail. If the tube reported so faithfully something they knew well, was it not credible when it brought them the sight of the invisible moons of Jupiter? No doubt of it, his spring trip to Rome ended in triumph. His friend, the painter Ludovico Cigoli, shared the view of the moon through Galileo's telescope. The artist's vision was deeply stirred. Cigoli was commissioned by the Pope to paint an image in the papal chapel of a great church in Rome. He chose to represent the Virgin, who is often shown as standing on the crescent moon. In the portrait, the Virgin was familiar enough, but the moon was entirely different. What had always been flawless in form was now a telescopic moon, mountainous, cratered, earthy, like the one he had seen in the telescope. With this painting, the instrumental view of the skies had entered the world of the imagination. But there was a deep conflict between novelty and authority. In the end, the old man was brought down. Galileo was required to pass his last years quietly in this house in the hills of Florence. A new structure to the heavens and more novelty year by year does not sound very biblical to us. Nor did it appeal to the conservative churchmen of that day. The story is often told. Finally, the Inquisition moved to silence Galileo, and he spent his last 8 or 10 years under a mild house arrest. Working to the last year or two of his life, he had to send his final book to be published in a Protestant land, and no longer in Italy. The tragedy is understandable. It's the tragedy of a man, and a social tragedy, the problem of human society. It was a time of great conflict, and the issues of substance faded away under the great issue of power and authority. But science did not suffer in that tragedy. The moons of Jupiter still dance, and the planets and the sun still spin, and the evidence the telescope brought is there still for all to see. Even in Galileo's time, say 1 generation after his death, there were a dozen observatories in Europe. Men with better instruments, able to see more detail and fainter objects, and to measure more carefully, tested and expanded upon what he had seen.
Okay, we're getting ready to start working on the objective lens, and the first thing that you need to do, as you know from reading the manual, is to grind the plano side to make sure it's absolutely optically flat. We do this because usually plate glass is not very flat, and my experience in doing many of these lenses is it can take several minutes or even a little longer to get the plano side really flat, and then of course you have to polish it. So we get ready to do this by sticking the one that's going to become the lens in the water so it'll stick to the paper, and then get ready with the tool. So this is going to be the lens and this is the tool, and we take the 800, the finest, and put just a little on it. Now the one problem we have with this very fine grit is it tends to clump near the center, and this is the grinding, again, about a 1/2 inch stroke, 1/3 diameter, and you go the star pattern and you rotate the tool on top the opposite way you're going to move the lens down there. So you just keep doing this, and as we say, you go through the grinding till the grit stops grinding. Now you can see how, maybe you can see this, I don't know, that the grit has tended to concentrate in the center. What you do is push it off to the side and start again. And this is just because the stuff is so very fine. Now you need to periodically rotate the bottom one in the opposite direction you're going. And you keep doing this for a while. And I'm going to flip this before I check it, just because to make sure that you do every once in a while grind with the lens on top and the tool on the bottom. This is to ensure that you don't start generating a curve, which we want this to be flat. So you must spend as much time with the tool on top as you do on the bottom. And don't worry about the stroke. There's a certain irregularity in this that you can, again, you see the grit wants to go towards the center. So just push it around. Okay, now we've ground on this for a while, and now is the time to see where the high spots and low spots are. And what you'll see when I do that is that the high spots will be ground dull and the low spots will still be shiny. And of course you keep this process up long enough so that it's completely uniformly ground. And again, since this is such fine grit, it tends to get moving towards the center. Okay, I'm going to stop and see how we're doing. There's no use spending more time on this than you have to. And if your arms are clean, you just wipe them off this way. Okay, now on the tool, I don't know if you can see this or not.
Okay, let me just
the tool is finely ground in the middle.
Just hold it there. Let me see if I can get it.
But the edges are still a little shiny.
Yeah, I think it's visible.
But it's actually quite flat. I'm surprised. This plate glass seems to be quite flat, much flatter than the usual stuff I've used. Okay, so the first thing we do, now you got you want to keep the ground side out, so I'm going to stick it to the shiny side. You stick.
Okay, now both go. Okay.
And then let some of it drip off. You don't need a whole lot. And then you plop it down and make sure you get it centered properly. Okay, the next thing I'm going to do, we have added, where's the bowl of ice? Okay, we have added some beeswax to this pitch to make it not so brittle. And I found as a result, to work with it, you got to cool it down. So what I'm going to do is cool this down and trim that. To do, this is a tool, and it will be the lap, is to put a collar down so that we can make the pitch lap. And we want the collar to stick up above the thing about a quarter of an inch. The pitch onto the tool and make the pitch lap. Now, what you want to do is fill it to the point where, and about a quarter of an inch thick, where the pitch is about ready to run over. You want it to be convex upwards so that the okay, that should do. Now I'm going to put some cerium oxide on this. Spread it around. Now comes the fun part. You push down and start going around.
Okay, hold on a second, it's hard to see this.
What you're trying to do is get the pitch to conform to the shape of the, in this case, flat. And I add some cerium oxide, and then using the same stroke as you did before. Now this is going to tug and pull on it because that tool, or in this case the lap, or no, actually the lens is on the bottom right now, and as I said, you want to switch back and forth, doing half the polishing with the tool on top, or I'm sorry, the lap on top, and then the other half of the time with the lens on top. And this is to make sure. Now the amount of curvature you would put in that lens with the 800 grit and with the polishing is essentially zero, but you may as well make sure it's as small as possible by having the tool on top and then the lens on top. So I'm going to give this about 10 minutes, and we can then see how well it's polishing. We have finished polishing the plano side, and I have taken both the lens and the tool and the lap off from their spindles and flipped the lens over. Now the one thing you got to be careful about, because both sides of the lens blank are now polished, make sure you don't put the wrong side, stick it on the tool or the spindle. And what I did, there was a scratch on the side that we're going to now work as the convex surface, and I used that. Now, of course, Ken and I will have written, you know, with ink, with a felt tip pen, the P side and the CV side and so forth. But of course, that may actually wear off. So be careful you do not put the wrong side stuck to the spindle, i.e. you want the side that you've just finished in polishing, the plano side stuck to the spindle. Otherwise, you'll obviously undo all the good work you did. So we're ready to go. We're going to use 220 carborundum because the curve we're generating is very shallow, and it should only take, based on my previous experience, 30 minutes or so, but you know, roughly, to generate the curve, and then we will show you how to test the focal length, measuring the curvature or the focal length of the tool, and we'll explain that as we go along, as explained in the manual. Unfortunately, the sun is not out today, so I could only start this process. So off we go. There's our lens. We're going to start generating the convex curve. Put some water. Oh, one other thing. Stick the ground side, the finely ground side of the tool onto the spindle. That will give you a little more grip because the other side, of course, as you can see, is still unground and totally polished. So, off we go with 220. You sprinkle a little grit. Woo, that's a lot more than 9/10
Okay,
sprinkle.
I just want to get a picture of that.
Okay.
Okay.
Now, we do the 1/3 diameter stroke. You can hear the grinding. And as you're supposed to do, you rotate the spindle of the tool. The tool is on top. What will be the convex surface is on the bottom. And by going with a 1/3 diameter stroke, you will be generating the curve, which would be quite shallow for this long focal lens. Now you can, as the grinding occurs, as we say in the manual, you will hear the grinding get softer and softer, and the grit is being ground down to mud, and obviously once it gets all ground down, it's not doing anything. And again, don't worry about trying to make exactly 1/2 inch or 1/3 diameter stroke. This is always going to have some irregularity and randomness to it, which is fine because that helps to generate the surface we want. You can actually see that there is, I don't think we can see it there, but there is a curve that is generating because there's light coming through.
Now remember, this is not the lens. This is the
tool. Now, the tool, the focal length of this mirror is going to be roughly 1/4 the focal length of the lens. So when we get where we want to go, this will have a focal length that we'll measure with this yardstick, and there's the target, which it will, the sun, this image of the sun. And what you'll do is, get this wet, and then you'll be moving this up and down until you get the best focus you can. As the focal, as the radius of curvature gets deeper, as the focal length gets shorter, you will get a better and better measurement. What we want is to, at the end of fine grinding, it'll be about 16 inches, and that'll mean that the lens has a focal length of about 60 inches, what we want. So unfortunately, because the sun is out, there's nothing more we can do, but this is how you're going to grind. And I will finish the grinding, the rough grinding and the fine grinding in the next day or so, and then we will start polishing, and when that's done, the main lens is done. Okay, we finished the lens. And polish it and taken it off the spindles, and now we're going to check the focal length. And you can see down there the image of the sun on the.
Okay, let me get down there.
And that's definitely out of focus. It's not real sharp. That's getting there. That's a good focus. We begin to go out. It looks like the focal length is around 62 to 63 inches, which is fine. As we say in the manual, it's very difficult to control the focal length with these long focal length lenses because just a little bit of work. Actually, I think it's around 62. I think it's between 61 and 62.
Now, one of the things we just might want to add is that focus is not a point.
No, that's the image of the sun.
Right, exactly.
That is an image of the sun, 1/2 inch in diameter, which is what you'd expect for this focal length.
Yeah.
So that's really a very nice image. The first part of the mirror cell, the lens cell, and this is the black piece that has the rim receded here, so we can have.
Show it on an angle.
You can see the.
Right,
okay, there's two pieces. Remember, for the cell, both of them are black. This is the one you want. So what we do, we put a little bit of glue. Now, right at the very top here. That wasn't very much. All right, that should do it. Now, shove this guy in. Whoops, that's very loose. So I'm going to put a lot more glue on there. You want it loose, but you don't want it that loose. All right, in we go. All right. And leave it about 3/4 of an inch out. And then we have to get rid of the extra glue. All right, now we're gonna have to let this set so it's completely glued. I gotta wipe this up. Stop it again a second.
So, okay.
Okay, the dew cap. We already cut this off earlier. This is the dust cap. As I said, keep these things that are in the tubes. You don't have to put that in there now. We've got the second part of the lens cell. You shove this in, but not all the way, because the idea here is very simple. When you slide this on, which I'm not going to do because that hasn't dried yet, you push it down and then this slides back and then puts pressure because your lens is going to be there. Now once this is dried, we'll put the lens in later, but I just want to show you how this is going to go. So now we're ready to fix the back end of the telescope. Now, if we've made all our calculations correct, this should slide down all the way and not hit the rings that we just put in there. If it does, then we have to trim a little off. There we go. See? Now we're perfect. Now what we're going to do is check one more thing. We're going to put the lens in and the eyepiece. I may have to go get the eyepieces and make sure that it's going to work. So stop a minute, Ken. I think your eyepieces are still on your tripod.
Okay, I'm filming.
Okay, so we're going to test, before we glue these tubes together, we're going to make sure that everything is correct, just like we tested to see if the inner tube would go in properly. So you lay the lens in that recessed part, and then again, you've got the ring so that when you put this down, it will push against the lens and hold it in properly. Now we are going to take this outside, first with the 2-inch lens, which will give 31 power. Make sure that it will focus perfect. Okay, we are set to go. Everything is the right length, and we can finish the telescope. So, next thing we take out the lens.
Okay. Let's just hold on.
So now we know that the measurements are correct, the focus is where it should be, etc. So take everything apart again. Be very careful that you don't do something to the lens. Pull the straw tube out. It already did. Okay, now pull it all apart. And now we're ready for the final gluing and assembly. So we start with the front piece, that's the back piece again. Now, first of all, I gotta measure and see how far it goes in.
Yeah. Okay, let's just hold on. Just show that this is.
Oh yeah, this is the split one.
Yeah, right.
Okay, there's banging up against there. So what I'm gonna do is put glue. Oops. On this, and again, speed is important. Not putting the glue on there, but when you shove this in, don't wait, because this glue isn't setting, but because it's moist, it adheres in a certain way. All right, now. Okay. I got to squeeze this together to get it started. Dang it. Okay. In we go. Bingo. That's in. Now wipe off the excess. You might need to wipe off the whole tube eventually because the glue gets on everything. Now we're going to do the back side. We do the same thing. Now we put glue and you don't need to make it all the way to the end because as you see the glue is going to get pushed up there. This, come on. Okay, now make sure you've got the right end. Okay, squeeze it together, slide it down, and away we go. There. All that has to happen now, you can check along the tube to make sure it is straight.
Here, you stay there. Hold on. Let me see.
That's very nice and straight.
Yep. Okay. Good.
You might want to twist it a little bit back and forth. Wipe the excess off. And in principle, your telescope is done. All it has to do is dry.
Overnight.
No, it just takes a little while. And now, we can go ahead and put the lens back in. Whoops, other end. Remember, the end that goes in is the end with the black paper all the way to the end. This is the end where the eyepieces go because the paper, the black paper does not go all the way. All right, that is it. The telescope is done and you can start observing with it once you've got the mount made.
Okay, let's get a long shot here. Okay, hold on.
And we're going to put it in. We already have a little kill it. Is sliding your telescope in here, and it doesn't make any difference which end you start on. You need to find the balance point though. The balance point is about there.
And you might want to mark that too.
Yep.
Yeah.
I'm going to do that with a pencil. Love filming me when I'm walking around, don't you?
Of course.
All right, this can be erased if you want to after.
No, they can see your observatory and stuff.
Oh, yeah.
This is the Helvelius telescope right here.
Here we go.
Yeah. Okay, back to Alan.
Here's my mark. There it is. All right. Whoops. That eyepiece won't fit through there. See how the eyepieces go in their little holder?
Yeah, the one side is tighter than the other.
That's fine, you want it tight. And then I have okay, now I need two other things.
The eyepieces. This is the whole Helvelius telescope that Alan built. This is his favorite scope. So, yeah.
As it turns out, this is the tie wrap that we use. I only have one, so I can only put it on one side. But you see what you do. Now, to do this properly, because you need to have, this telescope has to really be tight in here. And even though there's quite a bit of pressure, it's not enough. And to properly get it tight, I have to make sure I know which end. Because I don't know why. Okay. What I do is I bend it so that it goes around the corners. Otherwise,
yeah, that may not be long. Is that long enough?
Yeah, it's not.
Okay.
Well, wait a minute. Your yoke is wider than mine, son of a gun.
Yeah.
All right.
It'll work right now.
Yeah, it'll work right now. Basically, you have to see. It turns out that we made this too wide, and that's we'll correct that in the manual. This should be a little bit narrower. In fact, in the prototype over here, you see how this is done. This is a slightly shorter focal length, but I made this telescope some time ago, and it was the motive for making this one. So you tie these in and get it really, really tight. So that is your telescope. Now, let's see how it works. Wow. I also like to look at those rocks up there.
And you can sight along the tube to point it.
Now it'll be stiff in the beginning. Right now this draw tube comes out a little stiff. But here we go. Take a look, Ken.
Okay, hold on. Looks pretty good.
You have to be that far away?
Oh yeah, right there. That's where I have to be.
Wow. Let me see how far I am.
Yeah.
Because I thought my nose just touched this. Yeah, my nose just touches it, and then it's exactly the right distance.
Yeah.
You sure you're?
Yeah, that's where I got the full image.
Huh.
Well, I'm holding the camera too, so I need to put all that down to.
Well, go ahead. Yeah, we're done filming anyway.
Okay.
Ancient documents, check. Mysterious unopened boxes, check. Keith Moore, head librarian, check. We have everything we need for an objectivity video. What have we got, Keith? What have we got?
Well, we have here 3 very large lenses, and these are lenses from aerial telescopes made in the 1680s. So you can see they are inscribed, and the lenses themselves are rather nicely mounted, and these were made by Christian and Constantine Huygens, the great Dutch instrument makers and astronomers. And what you have here is a lens of glass, and it's mounted.
For July or for June, or what month is that?
Yeah, that's for January, I think.
For January. First things first, Keith, this is not the original mount.
It isn't, no. This is a later Victorian mount, and it was put on there by a Victorian astronomer called Warren de la Rue.
Okay, and we see this mount comes from
1856, so a couple of hundred years.
Yeah, and the lens has probably been remounted several times in its lifetime.
Another thing I'm noticing, Keith, is that the glass is like it's got lots of flecks and bubbles in it, and it's not it's not the sort of perfect glass I associate with astronomy.
Well, that's absolutely right. And something else you might notice about it, it's rather flat. It doesn't really look too much like a lens. It doesn't have much of a profile to it.
Yeah, you're right. It hasn't got that kind of concave or convex nature you would associate with something for bending light.
And this is just limitations of the glassmaking techniques of the time, but also it's to do with how they observed at this period. So this is part of a very particular kind of an instrument called an aerial telescope.
An aerial telescope?
Yeah. So we're very familiar with telescopes which have tubes. This one didn't. And you can see here, this is a 122-foot focus. You'd be standing 122 feet behind this with another lens, and you would be trying to make an observation with a telescope of that length.
That's extraordinary. So this piece of glass is 122 feet above us, refracting the light down to someone observing it way down below.
That's absolutely right.
Well, let's put down our 122-footer.
And let's have a look at the next one.
Fairly similar looking. Again, it says object glass, 170 feet, a much bigger focal length. But I also can't help noticing it says here, presented by Sir Isaac Newton.
So this belonged to Newton. He presented it to the Royal Society.
Oh, wow. But he got it from Huygens.
He did, yes.
So these weren't donated by Huygens as like museum pieces to say, remember me by this. It was more along the lines of, get to work, there's more work to be done with this.
That's right, so he made them in the 1680s, but this one was presented in 1691, this one slightly later, and the third one later again. So they had quite a long life as instruments.
Just think about this, people. Huygens, Newton, all used this, and now we're seeing it here. Now you're looking through it right now. Amazing. So we've got one more to open, last but not least. Okay, here we have it again. It says object glass by Huygens for a telescope of 210 feet.
Pretty big.
That's amazing. Just so I can say I held all of them. We'll hold this up to the window in a second so people can see all these little bubbles. Wow, real piece of history that.
We do have some drawings here. Here we have papers on large telescopes by Robert Hooke. So he says that was set up about the middle of the quadrangle of Gresham College, a mast or a pole of about 14 inches in diameter. And we can see a picture of it because he very helpfully drew one.
Oh, wow,
so
wow.
Here it is.
Oh, you can even sort of see the quadrangle too.
That's right. So this is Gresham College. This is the Royal Society's first home. And you can see there's a mast embedded in the ground here. Now you will see that this is an enclosed telescope. So it's not quite an aerial telescope yet. And these would be typically 20 foot or more in length. And reasonably stable, but they would tend to bow these instruments. So not ideal. And right at the back here we have a classic image of exactly how these things work. So here we've got the mast again, and it's a pulley system, so you can raise and lower the object glass, which is in this bucket arrangement at the far end of the telescope. And you can see that the observer is using a lens here, which is just tied by a piece of string to the business end.
That's amazing to see.